Well, ladies and gentlemen, today we're going to learn about simple harmonic motion. Now, sometimes we'll reference this as SHM, which is quite the opposite of SMH. Okay, so what is simple harmonic motion? Simple harmonic motion is a very special type of periodic motion. Periodic means that it happens, you can count on it to happen, and it's a oscillatory motion. Now, oscillation, you might have seen this mode on your fans, like when you turn on the fan during the summer because the AC is broken. There's a mode called oscillation, and oscillation means that it goes back and forth, and that is the main idea behind simple harmonic motion. It is a motion that goes back and forth, because there's a force called a restoring force that pulls it back in one direction when it goes a little bit too far. Okay, and the big idea here is that the restoring force is based upon the displacement from the very middle spot that it wants to be, and the restoring force is opposite of the displacement. So, for example, if we have an object that gets pulled in one direction, the restorative force is pulling it in the opposite. So if you pull something to the right, the restorative force pulls to the left, and vice versa. If you pull something to the left, the restorative force pulls to the right. Okay. All right. So here we have two examples of simple harmonic motion, and both of these are what we're going to be dealing with in AP Physics 1. On the left, you can see a spring oscillating back and forth, and on the right you can see a pendulum oscillating back and forth. It's important to know that the restorative force for the spring is based upon the spring force, and the restorative force for the pendulum is based upon the gravitational force. Alright, so let's go over a couple of terms and vocabulary that we can relate to our variables. So capital T is period with the units in seconds. So it's the duration of one cycle in a repeating event. So one period will be going from left to right and then back to the left. That will be one period. So if we go left, right, left, that'll be a total of 2 periods, and so on and so forth. Frequency. The unit for frequency is hertz, or we could also write hertz as 1 over seconds, and it's used to describe a rate. So basically how often something is happening. When we were doing circular motion or rotational motion, we called frequency revolutions per second or radians per second, and sometimes you might see it as cycle per second. Okay? So frequency is anything over seconds, and the equation is something that you can see down below. Frequency is equal to 2 pi over the rotational velocity, which is equal to 1 over the frequency. Okay. All right. Next up, we have amplitude, which is in capital A. Amplitude is the maximum displacement from the resting position, and the units for that is m for meters. So on the left, we can see an animation. Right here at the 0 mark is where the mass starts off. Okay, and then we pull it up. If we push it up to this max height, that's our maximum amplitude. So at that point, what the spring wants to do is it doesn't like being squished, and so the spring is going to push it along with the help of the gravitational force. It's going to pull it all the way down until it has a maximum amplitude in the opposite direction. Okay, and what we get is a very beautiful curve called a sinusoidal curve, and we're going to be seeing that shape a lot. We can also see the amplitude where we pull it down first, and so that's the maximum stretch, and then we release it, and when we release it, it springs all the way back up. And the important thing here is that the maximum displacement when you push or when you pull, it will always be the same in a theoretical situation. Okay, so let's take a look here. At the very top is the motion that we are describing with the three pictures below. We have figures A, B, and C. So at figure A, there is no displacement because we didn't pull it or push it in any one direction. So it's at the very, very bottom. So in this scenario, we can imagine that we did release it from the top and it is at the most bottom part of its swing. So at the most bottom part of the swing, it would have the greatest velocity because all of the potential energy got turned into kinetic energy. And so if all the potential energy turned into kinetic energy, then we can say that the velocity is the greatest. At that point, because there is no displacement or there is no amplitude, there is no restorative force. All right, and so section B is when we pull it back just a little bit or when it's at that height. So at this height, the displacement is greater than A, but less than C, okay, because it hasn't been pulled back all the way. And that is also proportional to the velocity for that point, okay? The velocity at C is the least, and we know that because at position C over here, that's at the maximum height. And at the maximum height, we have the greatest potential energy. And that potential energy turns into kinetic. And point B, or figure B, is right in between the greatest potential versus the greatest kinetic, which is at the bottom. Right? And we can see that the restorative force for position B is somewhere right in the middle as well. Okay, and last but not least, we have position C. And position C is where we first start off. We pull it all the way back, and so at that point, we have the maximum amplitude. At that point, we have no velocity, because at that point, we can say that there is no kinetic energy. At that point, we have the greatest restorative force because that pendulum doesn't like being pulled back. It wants to be at position A, but it's not at position A. And so the restorative force wants to do everything that it can to pull it back to position A. Cool. All right. Now, we see here three graphs, and it's important to have these graphs down in your notes because it helps us describe a lot of things. The very first graph is our displacement graph. So we have a position versus time graph, and so there's a couple of things that should be going through your head. For a position versus time graph, the slope represents the velocity. So if we take a look at time zero, at time zero, we have the greatest displacement. It's pulled all the way back. But that slope right there is a flat line, so we have no velocity. So if we have no velocity, that means it's at its max height because we have the maximum potential energy. And we can see that right there, okay? At point 0, we have no velocity because it's at the maximum height, okay? And at the maximum height, according to the previous slide, we know that the restorative force is the greatest, okay? And force is mass times acceleration. And if we have the greatest force, we should also have the greatest acceleration because we're not changing the mass as it swings back and forth. And we also notice, because for a velocity versus time graph, the slope represents the acceleration. And right there, if we were to compare time 0 versus right here, at that point, the slope is a flat line, so there is no slope, versus the very, very beginning where it has the greatest slope. So we can see that the acceleration goes from, a maximum value, and it eventually turns into 0 acceleration. So what I want you to do is, while you're copying these graphs down, try to make sense of the individual parts. For example, where they have the dotted lines, so I'll do this one with you, where t, at that point, we have the position is at 0, so it's at the origin, right? And at that point, it's in full swing. It should have the greatest velocity. And we take a look down here, it in fact does have the greatest velocity. And when it has the greatest velocity, when it's at the origin point, that means there's no restorative force. If there's no force, there should be no acceleration. And in fact, right there in the acceleration versus time graph, we see that the acceleration is 0. Okay, so take a look at this, copy it down, and try to make sense of it. We're going to be using these graphs a lot in class. Okay, so here are the variables that affect simple harmonic motion, and we'll be using these variables and these equations in class. So there's two different forms. We're going to go over the pendulum one first. So we see here that the period for a pendulum is equal to 2 pi times the square root of L divided by G. Okay, L is the length of the spring. L is also directly proportional to T. Of course, it's a square root proportionality. Okay? So if L increases, then the time has to increase. So what that means for us is that if the string length increases or decreases, then the period will follow suit. All right? So G. G is the acceleration due to gravity. This is very important because if we were to release a pendulum in a area where there is very negligible acceleration due to gravity, right? Some people might say space. We can see that there will be no pendulum motion because there is no restorative force. There's nothing pulling the pendulum down. But if we were to compare the period of this pendulum on Earth versus that on a planet or a satellite with little gravity or less gravity, we can see how it affects it. So let's say we were to take this pendulum and put it on the moon. If that were the case, then the period would, so we know that on the moon the acceleration to gravity decreases, and so the acceleration to gravity decreases because in the denominator, the period length would increase because it's a inverse proportionality. Okay, if one goes up, the other one has to go down. If one goes down, the other one has to go up. And so what that means is that the pendulum will take longer to swing back and forth. All right, next up we have the period for a spring. Now, what's interesting here is that for a spring, there is no gravitational constant, but we have a mass. We need to have a hanging mass and a spring constant, and the spring constant, which is designated as K. Okay, so mass and the period are directly related. Because they're both in the numerator on the opposite signs of the equal sign, and we have K, which is the spring constant, which is in the denominator, and that's inversely proportional. So K is the stiffness of the spring. So if we have a super stiff spring, and versus a spring that is not very stiff, kind of like a slinky, we can see how it would affect it. So if the spring constant decreases, that means the amount of time it takes for the pendulum to go back and forth would increase it, because there's the spring isn't pulling back on the mass as hard or pushing on the mass as hard. All right. So on this slide, we're going to take a look at what actually happens in the real world. So you will probably see this in your data if you take data over a longer period of time, and this is what we call the dampening effect or the dampened effect. And so what this means is that when you have a periodic motion or simple harmonic motion, it goes back and forth, there's going to be some kind of friction involved, or in case for a spring, there's going to be some thermal energy that is released. Okay, and so some of that mechanical energy gets transferred into thermal energy, and so the overall mechanical energy decreases. So when that happens, the amplitude decreases, the displacement. And so what you see in blue is the maximum displacement of the simple harmonic motion. You can see that it decreases. Okay, and in this graph here, the black box is the motion without any dampening effects, and the blue block is a motion with dampening effects. So you can see that the period itself, it stays the same. However, it's the amplitude that gets decreased. Great. So we're going to take a look at a couple of simulations. So let's take a look at a couple of simulations so we can see how different variables affect a pendulum's simple harmonic motion. So we have a motion that goes back and forth, back and forth. And so what we see here from this maximum angle to this maximum angle, that is our current amplitude. Okay, and if we were to clap along, and we can see the period. So I'm going to start off when the pendulum is on the left. So okay, so you can hear the period, and we know that if we increase the length of the string, the period should also increase. So let's try that. I'm going to increase the length of the spring. Okay, notice that the amplitude it should stay the same, but let's clap along for the period. Okay, we'll start on the left. Wow, much slower, and we could in fact use a timer. So one period is about 2 seconds, but if we decrease the length of the spring, or the string, we know that the period should decrease as well. Boom, about 1.4 seconds. Okay, so if I were to increase the mass, remember now mass isn't a part of pendulum motion, we should get roughly around the same period. So I'm going to change this to, let's change it to something I have better reaction time with. So we'll change it to 1 meter. Okay. All right. Okay, so that's about 3 seconds. I'll try it one more time. Okay, so that's about 2 seconds. And if I increase the mass, and we were to redo this trial, 1 period, okay, 2 seconds. All right, so we'll try it one more time. Okay, around 2 seconds. Cool. All right, so doesn't really change, right? But if we change the acceleration into gravity, we know that it has an inverse relationship. So let's go to the moon. All right, so if we go to the moon, we can see that 1 period, wow, look at that, 5 seconds. Is that cool? All right, now let's go back on Earth, but let's add a dampening effect. If we have medium dampening effect, we can see that over time, it should decrease. I'm going to increase it more to prove a point. Cool. All right, that's dampening. Awesome. All right, now let's try a spring. So if we pull down on the spring, okay, we have 100 grams. It oscillates back and forth. I'm going to slow it down so that we can clap along. Okay, and we can add a stopwatch. So we'll start at the bottom. All right, so that's about 0.65 seconds. But if I were to increase the mass, I think I started a little too soon. All right, so we can see how it changes it. And we could also see, let's add the 100 gram one. All right, so we're going to pull it down to about 40 here. All right, let's change the spring constant. So if the spring is hard, so we increase the K. Cool. We can see how that affects the pendulum's period. Okay. Great. Well, I hope you learned a thing or two. If you haven't gotten all of the equations down, please do take it down. We're gonna be doing these labs in class, so it'll be very helpful if you have all the equations and your notes ready to go. See you later. Bye bye.